Welcome to the viewers. Today we discussed an important theorem, convolution theorem, which is very important in solving many problems in Laplace transform as well as Fourier transform. Now here we discuss this theorem in Laplace transform. At first, in the domain real S is the parameter of the Laplace transform. It's a complex parameter which is greater than a1, and where in this domain Laplace transform of g1 exists, and if it will be g1s, Laplace transform of g1t, if it will be g1s, and in the domain real S is the complex parameter greater than a2, where Laplace transform of g2 is equal to g2s, and then Laplace transform of psi t is equal to g1s g2s. This is actually exist in the domain real S for maximum of a1 and a2. For here and here we condition maximum of these two, and in domain range is this, and where psi t exists, Laplace transform of psi t will be this. We have to prove this. And where psi t is the convolution of two functions g1t and g2t. Psi t is defined by psi t equals to integral 0 to t g1 tau g2 t minus tau d tau, alternatively 0 to t g1 t minus tau g2 tau d tau, where g1 g2 are exponentially order of e to the power a1 t and order of e to the power a2 t respectively at t tends to infinity. And so we have there exist two constant n1 and n2 such that mod of g1t is less than equals to n1 e to the power at, and mod of g2t less than equals to n2 e to the power a2t. So by the use of the inequality we have mod of psi t is less than equals to integral 0 to t mod of g1 tau into mod of g2t minus tau d tau. Actually this comes from the definitions, and if we are taking mod of psi t we are getting this result. And n1 and apply this theorem g1 tau and n2, then using the inequality conditions of the inequality, that means where we write here g1 tau is equal to n1 e to the power a tau, and g2 t minus tau means n2 e to the power a t minus tau. Using this result here, replacing t minus tau, so here also replace t minus tau, and substituting both these values here we get these results. And it's also clear integration with respect to tau, so we write here outside the terms of the integrations n1 n2 and e to the power a2t. Since here is inside tau, so we are writing in this way. Now after the integration we find this type of result, and if we breaking it, multiplying these two, we are getting this. Now using the condition, see if a1 greater than a2, then mod psi t is less than equals to this, because this will be neglected, and similar cases we getting this result a2 greater than a1. Therefore mod of psi t and mod of psi t less than n less than equals to n e to the power a2, where n equals to mod of n1 into by n1 into by mod of a2 a1 minus a2, and a is equal to maximum of a1 a2. We replace in this way. Now Laplace transform of psi t exists, so here we have done the existence of the Laplace convolution of the Laplace transform. We check it in the domain DLPA, and that is given by it is Laplace transform of psi t is equal to integral 0 to infinity psi t e to the power minus st dt. S is Laplace parameter, complex parameter, taking limit t tends to infinity, improper integral, so it is replaced by 0 to t psi t e to the power minus st dt. Now here we write dt e to the power minus st, and putting the value of psi t, that is integral 0 to t g1 tau g2 t minus tau d tau, and it's obviously it's clear integration with respect to t, so here t equals to 0 to capital T. Since t tends to infinity we have 0 to capital T from the range, and here from tau, integration with respect to tau. So tau is equal to 0, but here now tau equals to t. So we are taking rough pictorial representations. Here t and tau, this is a graph, and here t is a maximum capital T tends to infinity, and at t equals to tau to t equals to t. Now changing the order of the integrations, it's very important. Limit t tends to infinity, integral tau is equal to, here tau is equal to 0 to t d tau, and here for t equals to tau to t equals to tau to t equals to capital T, dt integration e to the power minus st g1 tau g2 t minus tau. Now if we replace t minus tau by t dash, let t minus tau equals to t dash, then t equals to t dash plus tau in this way. Now keeping here we replace it tau, integral tau equals to 0 to t d tau g1 tau, and t dash equals to, so what will be t dash? If t equals to tau, then t dash equals to 0, and t equals to capital T, then t dash equals to t minus tau. So here in the upper integral will be t minus tau dt dash e to the power minus s, and t will be replaced by t dash plus tau and g2 t dash. So finally we have limit t tends to infinity, capital T tends to infinity, integral tau equals to 0 to capital T d tau g1 tau e to the power minus s tau. If you break it, e to the power minus st minus st e to the power minus s into tau plus t dash. It will be tau plus t dash. It will be here, okay. It will be t is replaced by tau plus t dash, okay. So here it is minus s tau into integral t dash equals to 0 to infinity dt dash e to the power minus st dash g2 t dash. Now it's obvious result, taking the value at t tends to infinity, that means 0 to infinity. It's another type of steps that we skip here. It will be 0 to infinity if we put t tends to infinity, so result will be 0 to infinity, and it's clear it is a formula of Laplace transform, that is g1 is, and another is obviously 0 to infinity, it is another Laplace transform. Or better to derive the results and write the result once more. Just here we write integral 0 to infinity e to the power minus s tau g1 tau d tau, and another is 0 to infinity e to the power minus s t dash g2 t dash dt dash. So it's obviously clear, and there will be no problem, and that will be, we can write it as g1p and g2p. Finally we prove g2s, s will be the parameter, because since the parameter is arbitrary, whatever may be, we write g1s and g2s. We may write p here. If we write here p, then we consider every parameter as p. Now today we prove the convolution theorems, and in the next videos we will use these theorems in solving few applications in Laplace transform. Thank you.